What is 1, 1, 1?
Epsilon.
Epsilon. Epsilon star. What is 1, 3, 1? B.
Again.
So it's B union B. Which is B? So 1, 3, 2 is a B. Union. 1 to 2. From 1 to, I think we did this before, didn't we?
No, we didn't.
We did not do this? Is A. You already come to the A, right? So A.
Yeah,
2, 2, 2. B
Yep.
union. Star. 2, 3, 2. I don't think we did. Let's see if we can see it. Instead of reducing down to 1, can we figure it out as humans? 2, 3, 2, right? You want to go from 2 to 3 without crossing anything labeled 2 or higher. So the only thing you can cross is 1.
1.
Here to here. Well, there's no way to get there crossing 1 because you cannot go to 1. Right? So what is 2, 3,
Yeah.
2?
Yeah.
Only A. Oh, the only, what? You're allowed, oh, you cannot cross 2. I was going to say BA, but if you do BA, you're crossing 2. You're not allowed to cross 2 or higher. You're not allowed to cross 2 or 3. To go from here to here, and you cannot cross 2, you cannot cross 3. So you cannot take the loop, because that would be crossing 2. 2, 2, and just crossing.
It's only A.
So it's A. So by cheating here, let's just put A. Okay. So union substitute for that this. Let me write it here. Because we need to concatenate it with 3, 3 star, and then with 3, 2, 3. Right? So R 3, 3, 3. What is that? Instead of using the formula, right, I'll do it as a human here, trying to save time. What is 3, 3, 3? Well, I cannot cross 3, but I could cross 2 or 1, right? But to go from 3 to 3, there is no way, because there is no outgoing arcs, there is no way to get back to 3 by crossing 2 or 1, right? So the only way to go from 3 to 3 without crossing it is what? What is R3, 3, 3? A or B? Only A will do it, or B will do it. Of course, now, once I did that, my answer will be different than what the actual algorithm will give. Because the actual algorithm will not give you A or B there. He will reduce down to 1, and he will have something here that is equivalent to A or B. Yeah. Or empty string, you're right. A or B or empty string, yeah, yeah. You can go from 3 to 3 with empty string. Okay, and 3 to 3 is from 3 to 2, right? Is there a way to go from 3 to 2? There's no way. So what is 3 to 3? What?
3 to 3.
What do you say? I can't hear you. Do you say empty set? Yeah, the empty set. So actually we do not need to calculate this, guys, because right. This is 133, this is 333. So this one? Oh, that's part of the 133. This is 333, and this is 323. Okay? If I had done this first, I would say, oh, you don't need this. Can't, bother with it. So this whole thing is an empty set. So the final answer is A union A star A union E. That's the final answer. Because I took shortcuts, it would be different than the actual algorithm. Or maybe not. No, it will be the same because that is the empty set there. All the things we calculated will cancel out. See, these things where we took the shortcuts will cancel out anyway. Of course, this is equivalent to AB star. So that's it, that's the algorithm. Automaton, here's the language. Turn it on.
This one?
I got it. This loop. We have algorithms to go around, compared to one to the other.
Sir?
Yeah.
By FSA you meant NFSA? Is it a
What?
we did a algorithm for FSA to a regular expression, right? Like just now.
Yeah.
So this finite state machine, automata is a NFSA? Is it?
The what?
Is this a non-deterministic finite automata?
What do you mean this?
The one which we did right now. Is it algorithm from?
No, we took it.
Because we had epsilons in the answer.
No, we had epsilons in the regular expression. You're allowed here, A star, B star, union, E, you're allowed epsilons in the regular expression. Epsilon is a string.
So it's from DFSA to regular expression, the one which we did right
now. Yeah, right, to regular expression. Okay, now a language is regular if you can describe it using a regular expression, which is equivalent to saying you can build a DFSA for it that will accept it. That's exactly the language he accepts. Right? Everything else outside the language is the complement is illegal. Or if you can build a non-FSA that accepts it, the language is regular. So you can describe a regular language by any of those three ways. You can give an algorithm, these are algorithms, for finding which strings belong to it or not. Or if instead of an algorithm, which is a FSA algorithm, only if statements, and states, current states. Or you can, it's regular if you can describe it instead of natural language, right? Using a regular expression. This is a way to describe the language. A regular expression is not an algorithm, it's a description. Right? All the strings in AB star. Well, okay. All the strings that look like that. So now a question is, are all languages regular? Or are there some languages that are not regular? If everything was regular, we would be in good shape. Because any problem you can solve can be reduced to a language problem. So you have a problem to solve, right? Solutions can be patterns, strings of symbols. So that's what a solution is like. Everything reduces down to a sequence of symbols when you're solving a problem, right? So everything reduces to a string in a language. Okay? If all languages were regular, this means all the algorithms we will ever need as you're solving problems will be these guys. Which means all I need is programs with the if control structure in them, okay? And then a current state counter to keep track of changing states. So I have like a clock, state, 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 you're changing the states, and you just read from the input one by one and process it. And you only need to go through the input once. You don't need to rewind to the tape or anything like that. Okay? Well, unfortunately, this is not true. Not every algorithm is as simple as that. There are some languages that are not regular. There are some algorithms that are not FSAs. Here's an example. Take this language. All strings of A's followed by B's, but equal number of A's and B's. Take all these strings. This language is not regular. If I ask you, I can ask you confidently, even though I don't have $1 million, okay, I'll give you $1 million if you build a DFSA for me to recognize this language. I'm going to offer you that, because I know you cannot do it. It's not possible. This language is not regular. See, a problem with FSAs is what? They don't have memory. As you're moving around the states, I see an A, I go there. I see a B, I go there. If I ask you, where were you 3 steps ago? Do you remember which state? You don't remember, do you? You did not store it anywhere. Right? What was the symbol you just saw 3 steps ago? Well, I don't know. I just used it to move and threw it away. It's a local algorithm. I only know the current state. I know where I'm now. I have no clue where I was. I don't know. I forgot it. I updated my variable current state. Right? To do this problem, as you're traversing the tape, what do you see? An A. An A. You need to remember how many A's you saw. The FSAs do not have the ability to remember that, to have memory on the side. Of course, this is not a proof. There is a way to prove that, a set is not regular. A problem cannot be solved with an FSA type of algorithm. There is a lemma called the pumping lemma. Okay? And you use it to actually prove things like that the language is not regular. So next, let's talk about this pumping lemma. Okay, here is the first version of the pumping lemma. It says, it's a theorem, right? If a language is regular, then for sure you should be able to find there are, okay, 3 strings, X, Y, and Z. With Y not being the empty string, and with the property. So if it's regular, for sure you can find 3 strings that have this property. Y, X, Z is in the language. Oops, that should be an end here. If n is 0, y to the 0 is the empty string. So you can find x, y, z 3 strings with a property. X, z is in the language. X, y, z is in the language. X, y squared z is in the language, which is x, y, y is in the language. Y cubed z is in the language. To any power is in the language. You remain in the language no matter how much you pump the y. That's why they call it a pumping. Right? That's what the theorem says. And it's easy actually to see that this is true. If it's regular and infinite, I'm sorry, I forgot it. If the language is regular and infinite, this does not hold true if the language is finite, of course. Okay, why is this lemma true? Well, what is if a language is regular, right? Then there is a regular expression that defines it, right? Because that's what regular means. Well, what's a regular expression? You have symbols in it. You have the union sign and the star and concatenations. Maybe something like that. Okay, if the language is infinite, then you must have at least one star somewhere in the expression. Because if you have no stars at all, it will be finite. What's this? That's the string BA or the string B, two strings. Without stars, the language is finite, correct? It's this string or that string. So if the language is infinite, that's where the infinite comes in. In the language expression, in the language expressed as a regular expression, somewhere along the line, you must have something starred, a quantity starred, right? So the language will look like that. Okay, but then, can you find three strings with this property? Yeah, where will you pick your y? Whatever you're starting, pick a string out of here, and that's the string y. So pick a string out of what's in here. Since the language is whatever y star,
Sir?
y squared, y cubed, you're always in the language, including the empty string, y to the 0. What?
You said y can't be epsilon, right?
Huh?
Y is not equal
Cannot
to
be epsilon.
So
Yeah, so but you will have a non-epsilon quantity starred somewhere. Otherwise, the language will not be infinite.
But if n is 0, then what is the value of y?
Y to the 0, a string to the 0 is e. The empty
But
string.
y is not equal to epsilon, so how can we take it?
Yeah, what is, take the symbol a. Okay, what is a squared? A. Okay, a to the first, a. Okay, a to the 0. We have to define that somehow. We define it as e. In number theory, right? What is 3 squared? 9?
9.
What is 3 to the first? 3. What is 3 to the 0?
1.
1. What is 1?
Identity.
The identity of multiplication, of the operation. X times 1 is X.
Then
E is the identity of the concatenation operator. That's why we do like that.
Condition,
Huh?
why are we having that condition that y is not equal to e? We should not have that. Because y is taking the value of
The
e.
theorem says you can always find a y that is not e. X could be, z could be. For example, if the language was this. B star. This is a regular language, right? It's infinite.
0 more b's.
Can you find an x, y, z with this property? Yeah, what should you put x to be? You can put x to be
Epsilon.
empty. You can put z to be empty. And y b. Right? Is it true that e, y to the n, e is always in the language? Y is b. Right. It's always in the language. But the theorem says y, you can always find a way non-epsilon y.
So is the string xz recognized by the language?
Xz should be recognized, yeah.
Then in that situation, y is taking the value of epsilon, right?
Right.
Then how are we having that condition? We should not have that.
But if you change this, if you take this out, this is a different theorem. This says you can find x, y, z, right? That do that. Right? So if y, I can always pick y epsilon, this will always be true. So every language will be regular. This is worthless if I eliminate that. Okay. If y could be epsilon, this could be, let's say you have this, right? We'll pick y e epsilon. Epsilon to the n, e to the n is always e, okay? So pick x is a, y is b. This is always in the language? Yeah, it's always in the language. I want this. You will see why I want this. Because the way you use this theorem is to prove that something is not regular. So this is very important. Not only you can find x, y, z so that this is always in the language. I mean, if y is allowed to be epsilon, why you even bother to state this? You can do this not only for regular languages, for any language I show you, you can find x, y, z. It doesn't matter what the language is. I always pick y to be epsilon, e. Right? And I'll pick x to be something in the language, something else in the language, part of the, you know. So that will be a worthless theorem. No matter, not only if the language is regular, you can find them with ye. For any language, you can find x, y, z with y equals to the empty string. For any language. But for a regular language, you can even find a y that is not the empty string that does that. And that will be the y inside one of the starred quantities. Pick that y. Then when you bump it, since the expression is star, of course you will always be in the language. Do you follow?
The other reason could be that
What?
if y is epsilon.
So the question is this regular? Okay, you prove that it's not regular using the by contradiction and using this theorem. You say, if it was regular, then you could find. Then sit down and check out all the cases and prove that you cannot find such strings. That contradicts the theorem. So in this case, you say, if, let's say this is L. If L was regular, then by the Pampi lemma, you could find an x, y, and z with y non-empty. That's important. Okay. Okay. And with the property that you're always in the language, no matter how much you found y. So if this was regular, you can find x, y, z. Now, let's concentrate what the value of y could be then. Okay. For n equals 1, this has to be in the language. And for every n up here, this has to be in the language, right? But x, y, z must be in the language, which means x, y, z must be a sequence of a's, say IA's, followed by the same number of b's. So if I could find those three things, those three strings, since x, y, z has to be in the language, what could y be? Well, x, y, z has to be that. So maybe x is some a's, and y is some a's, and b is the rest of it. B is a's with b's. So what are the options for y? You have to choose a y, right? So you're always in the language. What can you choose as y? A number of a's. Okay, so y could be a number of a's maybe. But if y was a number of a's, when you take x y squared z. Is this in the language anymore? What did you just do? X is this number of a's. Z is what a's are left with the b's. And y is a number of a's. Now, this is x, y, z. Right? Now, you take x, y squared z. What happened? You doubled this number of a's in the string if you square the y. Did you ever change the number of b's? No, z it was not squared. So if x, y, z is in the language, x, y squared z will not be in the language anymore. Why? You have more a's than b's. It's not in the language. Well, so y could not be a number of a's. It's just rejected in that case. Okay. Well, what else could be? Can you choose for y? When you don't choose a number of a's, maybe some of the a's with some of the b's. Okay. So x is a's, y is some of the a's with some of the b's, and z is the leftover b's. Okay. So the second case, could y be some of the a's followed by some of the b's? Okay. No, because if you square the y, what happens? X is the same. X is a's. Let's say y was AAB, and you square it. You get AAB, AAB. You introduced a's after the b's. You screwed up the order. The language is not allowing any a's after the b's. Right? So if y was that portion of it, as soon as you square the y, you're not in the language anymore.